So the last speaker today is Rosengarten from Einstein Institute of Mathematics, who will speak about Tamagawa numbers of linear algebraic groups over function fields.
Okay, thanks for the introduction, and thanks to the organizers for the invitation to speak. It's a pleasure to be here. Yeah, so I'm going to talk about Tamagawa numbers of linear algebraic groups. We're generally over global fields, but I'm going to concentrate on the function field setting. So let me first state what those are. So let's say K is a global field. Okay, so it's either a number field or the function field of a smooth projective curve over a finite field. And let G be a connected linear algebraic group over K. Okay, so like a Zariski closed subgroup of GLN, and it's connected and smooth. So Tamagawa observed that there's a canonical left, let's say, Haar measure on the adelic points of G. Constructed as follows. Okay, so I mean, a priori, this is a locally compact topological group, so you know that it has some sort of Haar measure which is unique up to scaling. And the point is, he was able to pin one down canonically. Okay, so what you do is you say, you choose a top degree left invariant differential form omega on G. Okay, and the way you choose this, right, is you just take an element of the top exterior power of the cotangent space of the identity, and you translate it around. And that's how you get all the left invariant ones. I mean, that gives you one, and that's how you get all of them. I could say non-zero. Okay, and then, so for each place V of K, well, let's say non-Archimedean. You can also do something at the Archimedean places. So for each non-Archimedean place V of K, you choose the Haar measure on KV, the completed local field. Okay, whatever. On KV, let me call it maybe mu V, such that mu V, the ring of integers, is 1. Okay? And now, this Haar measure, together with this differential form, gives you a left, because I said left invariant, Haar measure on the KV points of G. Okay, and the idea, roughly speaking, is you just take the product of all these measures. So let me call this maybe mod omega V. Okay, and then you have is, not quite, but roughly speaking, the Tamagawa measure is, let me put in those quotes, is the product of these measures mod omega V. So you take some product measure on the, so this is on the adelic points of G, which are some restricted product of these local, these local points of the group. Okay, so this isn't quite correct in general. First of all, there are constants, so normalizing constants, which we won't worry about too much. There's also an issue if G has non-trivial characters. So if G has some map, non-trivial map to GM, then this product won't converge. So the reason for that, I mean, you can see it in the case, let's say G is GM. And this sort of illustrates the problem. So for GM, your top degree differential form is dt over t. This is your invariant form. And so, well, the problem is, let's suppose, I mean, what does it mean for this measure to converge? Roughly speaking, you would want that the product of, so this should be, you know, roughly speaking, this should be the measure of the product of, okay, this is an abusive notation because I haven't chosen integral model, but the measure of this product of integral points should be something like this, and you want this in particular to be finite and non-zero, right? Because this is some non-empty compact open. Okay, so in the case of GM, what happens is you're taking the product of the measure of GM of ZP, which is just ZP cross. This is GM of ZP. So what is this? This is the product. Well, let's do the case k equals q for simplicity. So product, and we'll look at the finite primes because whatever, we're interested in the infinite product. We're interested in the convergence property. So you take the product over all primes p of the integral over zp cross dt over the value t. And so what is this? Well, the integral, I mean, on zp cross, the absolute value t is 1, right? The p-adic absolute value. So this is the integral over zp cross dt. And so what is this? Well, zp is divided into p congruence classes, each of which has measure 1 over p. And this covers exactly p minus 1 of them, the non-zero residue classes. And so this is just p minus 1 over p. This is 1 minus 1 over p. And so if you take this, this is the product over all p of 1 minus 1 over p, which diverges to 0. So that's bad. So what you do is you insert some convergence factors. So this product here looks like an Euler product. And so you just basically insert some local L factor. So instead of the product of mod omega v, you have to take the product of mod omega v times some local factors associated to the character representation of G. So G hat, this is, well, let me put it this way. So G hat is the representation given by, you have the Galois group of Ks over K acting on, you take the character group of G. So, well, let me put it this way. Oms G to GM over Ks, the separable closure. And you have this Galois representation, and it has local L factors, and you just insert them as convergence factors to make everything work out. And then there are normalizing constants. OK, let's see. OK, great. So now the Tamagawa number of G is essentially the following. So you take the Tamagawa number G. This is the just notation. And this is the volume of the following quotient. OK? So this quotient space is something that comes up a lot. If you've worked with automorphic forms, it comes up all the time. It's a very important space. And we take its volume, and this is, of course, with respect to the Tamagawa measure. Again, I'm sort of lying here. If G has non-trivial characters, you have a problem, because if I have a character chi, that induces a map from the adelic points to the GM of the adels, which is the idels. And that contains, so the kernel of that contains G of, right, so this composition is, well, OK. This composition, let's see, so you have the norm map to R plus. So this is the map which sends an adel to the product of the absolute values. OK, and this composition is just the trivial map, because G of k lands inside k cross, and by the product formula, any element of k cross has absolute value 1. OK, so in particular, this this map is, for example, over number fields, this composition will be surjective. And over function fields, the image will be a lattice inside R plus. So the point, a co-compact lattice. So the point is that the image here is really big. It's too large for this quotient to have finite volume. So instead, you look at the norm 1 adelic points. which is defined to be, you just take the kernel of all these maps associated to a character chi. So the intersection over chi from G to Gm of the kernel of this map, which I'll call the absolute value of chi. Okay, that's just a definition. And it contains G of k by the product formula. Okay? And now, okay, there's at least maybe a chance that this thing, this quotient of this by that will have finite volume. And the real definition now is, so this is fake. The real definition is you take the volume of this quotient. All right. And I guess one other thing I should mention is that whereas the group, if you take the full group of adelic points, this is not necessarily unimodular, so there's a difference between left measures and right measures. Right? At the beginning, we chose a left invariant form. We could have picked a right invariant form. This subgroup is actually unimodular. And so it's always unimodular, and so the left-right distinction disappears. So this is totally canonical, no choices, this number. OK, so this is the Tamagawa number of G. Great. So maybe I should mention, OK, so, well, what is the significance of this? These numbers. All right. So I'll illustrate it with an example. So suppose that Q is a positive definite integral quadratic form. So we're over the integers now, just the usual integers. OK? So you can ask which forms, well, OK, one question you might ask are which forms are equivalent, which quadratic forms are equivalent to Q over the rationals, right? So this is answered, I mean, a perfectly satisfactory answer is given here by the Hasse-Minkowski principle, which says that, so it's if and only if it's equivalent over, OK, so it's positive definite, so there's some condition over the reals, and each QP. So it's just determined by, so two quadratic forms over Q are equivalent if and only if they're equivalent everywhere locally. OK? But then you might ask, OK, so we have an integral form. And you could ask, well, which forms are equivalent over the integers, not just the rationals? OK. So of course, if they're equivalent over the integers, they better be equivalent over Q. And that's equivalent to being equivalent over R and over each QP. But OK, so you're saying, so basically it's equivalent to some local stuff, local conditions. Well, let me put it this way. So it's equivalent to it over, so really what you're asking here is, given a form, an integral form, equivalent over Q, because that we know how to answer, when is it equivalent over the integers? OK. So then, you know, there's this classical definition of the genus of a quadratic form. So the genus of Q is just defined to be, it's a set. It's the set of, well, integral forms equivalent, well, let's say Q equivalent to our quadratic form Q up to Z equivalence. OK? And it's a very classical fact that the genus of Q is a finite set. OK? So now there's a somewhat less classical, but still classical formula for computing the size of the genus of a quadratic form. Okay, and it's called the Ziggo mass formula. And what it does is it says if I have a quadratic form, it doesn't count exactly the size of the genus, but it counts a weighted size. So you have a sort of stacky size. Okay. So the Ziggo mass formula this says that, okay, so if I want to compute the sum over, let's say, Q prime in the genus of Q, so if I were computing the size, I would just add 1, right? But this is a weighted, a stacky size, so you take 1 over the size of the automorphism group of Q prime, okay, instead of just weighting by 1. And it expresses this as an explicit product of zeta values. And actually, they're zeta values at positive even integers, so we actually know what they equal on the nose. But at any rate, so this gives you a nice way of computing what is the genus of a form. You just find enough equivalent ones that are equivalent over Q, but not necessarily over Z, until you've maxed out, until you know this sum gives you what it should give you. And you know, if you're wondering, I mean, this is, I think, interesting in its own right, but if you're wondering why you might care about this, there's a theorem which says that, so suppose I have an integer n, and I have an integral quadratic form q, then n is representable by q. So e.g. q could be x1 squared plus x2 squared plus x3 squared plus x4 squared, if you want to prove the Lagrange 4 square theorem. So n is represented by q. Sorry, stated that incorrectly. If n is, so I mean, of course, if it's going to be representable, it better be representable everywhere locally. So it says if n is representable by q everywhere locally, so I mean here integrally representable, then n is representable not necessarily by q, but by some q prime in the genus of q. So for example, if you prove a quadratic form is unique in its genus, then an integer is representable by it if and only if it's representable everywhere locally. Okay? So now, how does this connect to Tamagawa numbers? Well, the point is that the Ziggo mass formula here is equivalent via some very simple calculation, nothing deep here, to the statement that the Tamagawa number of this group, so you take the special orthogonal group of your quadratic form Q, that's a connected linear algebraic group, you can compute its Tamagawa number. And so this is equivalent to the statement that this equals 2. And I mean, actually something that's maybe a little surprising is this doesn't depend in any way on the quadratic form Q. It's the same for all positive definite integral forms. Okay. Another example, maybe before I go on. So if you want to compute the volume of, so you have SLN of R, and then you have the action of SLN of Z, and you might say, okay, I want to compute the volume of this fundamental domain. So there's a formula for that. It's just, again, a product of zeta values up to zeta of n. And this statement is equivalent to the equality Tamagawa number of SLN, this is over Q, equals 1. I don't know. I mean, well, actually, I mean, my guess is no, because I think he was earlier than that. But, yeah, but I mean, anyway, but like this is, I mean, the equivalence here is nothing, like there's nothing serious in the equivalence here. It's like some little, he basically proved it, yeah. Yeah. I mean, this is, you know, how one would verify this is you say, oh, well, it's the same as the single mass formula, and then, yeah. Any other questions? Okay. So the point of all this is hopefully I've convinced you that these are numbers which we should want to compute. Okay, so I should also mention, well, so Weil's conjecture. So this is not the Weil conjectures, but this is Weil's conjecture on Tamagawa numbers, which is that if G is simply connected over a global field, then the Tamagawa number of G is 1. Okay, so that's like SLN as an example. It's simply connected, its Tamagawa number is 1. This is over any global field. Okay. And I should mention, so this was proved by Langlands. I mean, they built on work of others, but the three big names are Langlands, Lai, and Kottwitz. In like the 80s, a series of works over number fields. And by Brian Conrad over function fields. And that's in, I think, 2012. I should also say, actually, it's not a priori clear from the definitions that the Tamagawa number of G is always finite, right? Like, we had to restrict to this group of norm 1 adelic points for it to have any hope of being finite. But the fact that it actually is finite is non-trivial. And I should mention this theorem. Tamagawa number of G is finite for any connected linear algebraic group G over a global field. So this is due to... No, sorry, you're right. No, I mixed up these two things. Sorry, thank you. Yeah, no, this was proved by Gates. Yeah, no, that's a big mistake. Yeah, it was proved by Gaitsgory and Lurie. And that was in like 2015, I think, actually. Yeah, thanks. But this theorem was, OK, so this is due to Conrad over function fields. And this is 2012. And then much earlier, it's due to, let me see, is it Burrell and Harishchandra, I think? Yes. So and then Burrell, Harishchandra over number fields. So this thing always is finite, so it's reasonable to try to compute it. This is in like this is 63, I think. Yeah. OK. Great.
So does Weil's conjecture imply that theorem?
No. Well, OK. I mean, well, OK, via a series of arguments. Yeah, yes, via a series of arguments it would. But of course, I mean, Weil's conjecture is a much more refined statement than just saying that this thing is finite, right? Like the proof is finite is much easier.
Right, so what I'm saying is that everything would have a finite fundamental group, and so then...
It doesn't follow immediately from that statement, but okay. You can give some devisage, and yes, ultimately it would follow from that, yes.
So somehow the Weil's conjecture is a more general statement, or more refined information.
It's much more refined. That's what I would say, yeah. Sorry, what?
What is G in that theorem? Is it the same as in the other?
This theorem? Yeah, G is connected linear algebraic over a global field. Yep. Sorry. Oh, wrong one. Yeah, sorry, what were you saying?
I guess even for a torus, it doesn't have a finite universal cover, so.
Yeah, OK. Yes, sure. Right. OK, so the next thing I'm going to talk about is that Sansuc in the 80s found modulo some results which weren't proven at the time but have since been proved, including, for example, Weil's conjecture. Gave a simple formula for Tamagawa numbers of linear algebra, well, let's say reductive groups over number fields. So there's a theorem, Sansuc, and this is sometime in the 80s. I don't know exactly when. If G, what?
Probably 81.
OK, 81. Fine. OK, thanks. If G is connected reductive over a number field, then the Tamagawa number of G is the size of the Picard group over the size of the Tate-Shafarevich set, where, OK, so I mean, many of you probably know what these things are, but I'll just define them. So the Picard group of G is, as usual, the group of line bundles on G up to equivalence, up to isomorphism. Oh, that made it worse. And the Tate-Shafarevich set of G is, so if you study elliptic curves or abelian varieties, you've seen this before. But here, instead of a group, it's just a pointed set because G is not necessarily commutative. So it's the kernel, this global to local map. OK, so it's the G torsors over K that everywhere locally have a point. And again, OK, so the finiteness of pick G is true, but it's not a very deep fact. It's something that, you can prove it. I mean, it's not trivial, but I wouldn't say it's very deep. The finiteness of SHA, that's a lot deeper. So SHA of G is finite for any connected. Well, actually, you don't even really need connected, to be honest, but I'll just say it, whatever. Linear algebraic group over a global field. So this is due to Borel and Serre, I think 1964. Yeah. Over number fields. And Conrad again, the same 2012 paper, Compositio paper, over function fields. And of course, this is completely open if you say G is an abelian variety instead of a linear algebraic group. All right. So, OK, so because these two things are finite and this is finite, this all makes sense. And this is Sansuc's formula. Tamagawa number is the size of pick over the size of SHA for G connected reductive over a number field. OK. So the remark I want to make here is that Sansuc's formula for linear algebraic groups, connected linear algebraic groups over number fields. So here I really am saying number fields, not function fields. OK, so Sansuc's formula for connected linear algebraic groups over number fields holds without any reductivity assumptions, and that's easy to show from the reductive case. OK. So why is that? Well, suppose G is a connected linear algebraic group over K, which is a number field. So then you have the K unipotent radical of G, which is, right, just as usual, it's the maximal smooth connected normal, this is really the key point, unipotent K subgroup G. So unipotent just means it's a Zariski closed subgroup of the group of, well, it can be embedded as a Zariski closed subgroup of this group of upper triangular unipotent matrices. That's where the name comes from. OK? So this is the maximal smooth connected normal unipotent K subgroup. So now you have, because it's normal, you have this exact sequence where H is just the quotient. And this H is what's called pseudo-reductive, just by design. Because this is the maximal smooth connected normal thing, the K unipotent radical of H is trivial, just by definition, essentially. So where this holds. OK. So this condition is called pseudo-reductive. OK, and so why is it called pseudo-reductive as opposed to just reductive? Well, reductive, by definition, means this holds geometrically. It holds over K bar. Right? So to be reductive means that the K bar unipotent radical is trivial. And pseudo-reductive just means the K unipotent radical. OK, so then the question is, well, why do you hear so much about reductive groups and you don't hear so much about pseudo-reductive groups? And the reason is, well, let's put it this way. So if you take the K unipotent radical of G, G is now some connected linear algebraic group, like, say, this one, whatever, and you base change to K bar, that's still a smooth connected normal unipotent subgroup over K bar of GK bar, right? So by definition, it's contained in the K bar unipotent radical. This is just by definition. This is the maximal one, and this is a particular one, so it's in there. I should say there is the maximal. It's unique. That's a fact. OK. So if K is perfect, well, OK, first of all, let me say this thing is what's called a characteristic subgroup of G, or of GK bar. It's preserved by all automorphisms of G. And so in particular, it's preserved by the Galois group. So if K bar over K is Galois, and this, of course, is the same thing as saying K is perfect. So that's certainly true for number fields or any characteristic zero field. Then we have an equality. Right? So the K unipotent, so this equals this. OK, so that in particular means that pseudo-reductive equals reductive over perfect fields, like over a characteristic zero field. So usually people don't worry as much about imperfect fields, so they just think about reductive groups, okay, because they're the same as pseudo-reductive groups. All right. So if K is a number field, or really any perfect field, actually, so you could just say perfect, then H is reductive. And one more thing goes well if you're over a perfect field, like a number field, which is, so this group is, of course, unipotent by definition. So over a perfect field, every smooth connected, I'll just omit that, every smooth connected unipotent K group is split unipotent. So what does that mean? That means that, so let's say U, that means there's a filtration. So, U naughts, well, let's say this is 0, contained in U1, contains, well, normal, contained in UN, which is U, such that, so i.e., this is the definition of split. There exists filtration like this, such that UI plus 1 mod UI is K isomorphic to GA, the additive group. OK? So the point is split groups are extremely simple because GA is a very simple group, and if you can filter something by a group as simple as GA, you can, in terms of basically everything that you want to know about it, or at least, for example, from a cohomological perspective, you know. It's very simple. So over a perfect field, this is split unipotent, and this is reductive. And so that allows you, well, OK. That means that all three of the quantities appearing here in the Sansuc's theorem are the same for G as they are for H. So they have the same Tamagawa number, the same Tate-Shafarevich set, the same pick. Everything is the same. So the general case of Sansuc's theorem over number fields follows from the reductive case, just by these general facts. So over function fields, which are, of course, imperfect, right? If you take like FQ joint T, that's very imperfect. T is not a Pth power. So over imperfect fields, this all goes horribly wrong. First of all, unipotent groups need not be split. They're very complicated unipotent groups. So I'll give an example now. And the second thing that goes wrong is because K bar over K is not Galois over imperfect fields, the K bar unipotent radical and the K unipotent radical need not agree, after base change.
What's the definition of a unipotent group? Normally, for me, that's the definition. So.
No, so the usual, OK, well, so my definition, so OK, the correct definition of unipotent group is it's a Zariski closed subgroup of the group of upper triangular unipotent matrices for some n by n upper triangular. Over perfect fields, that's the same as that other definition.
So here you are smooth connected, maybe?
Yeah, OK, so I said I'm omitting, smooth connected. Right, yeah. Yes. OK. So, right. So over imperfect fields, unipotent groups may be non-split. That's the first problem. And the second problem is pseudo-reductive does not equal reductive. OK. So All right, so here's an example of the first phenomenon over any imperfect field. So let's say that K is imperfect. And let A be a non-pth power of K. It's an element of K that doesn't have a pth root. That's what it means to be imperfect, that there is such an A. And so now you can consider the group y to the p, well, I mean like capital Y to the p is x plus little a x to the p inside of GA cross GA. And of course, by this I mean K has characteristic P. And because K is characteristic P, this is a genuine subgroup of this. And I'll leave it as an exercise to check that, let's call this U. U becomes isomorphic to GA over, not over K, but over K adjoined A to the 1 over P, over this purely inseparable extension. It is not isomorphic to GA over K. One way to see that is, OK, if it were isomorphic to GA, they'd have the same regular compactification, which is P1. But the regular compactification of this, you can check that this thing is regular. So y to the p is x z to the p minus 1 plus a x to the p. So this is the regular compactification of U. And the point at infinity is not rational. If you set z equal to 0, you have to take a pth root of a to make this rational. Okay, so this is not, well, the point at infinity, the point, let's call this U bar. So the point, so there's a unique point of U bar minus U. This is not K rational. So this group can't be K isomorphic to GA. It can't even be isomorphic to the affine line, although that's equivalent, but whatever. OK, so this, and there are much more complicated examples than this. Oosterlee has a whole paper from 1984, I think, in which the whole point of the paper is computing Tamagawa numbers of unipotent groups. So this is a completely trivial question over number fields, but over function fields, it's much more difficult. OK. And so, OK, the second thing, so again, over any imperfect fields, pseudo-reductive and reductive are very different notions. So for example, maybe here is one of the simplest examples. If K prime over K is finite, non-trivial, purely inseparable, so it's a purely inseparable extension of K, which exists because K is imperfect, then the Weil restriction from K prime down to K of GM, this group is pseudo-reductive, but not reductive. OK. And there are many more examples and many much more complicated examples than this. Yeah?
So could you define unipotent simply as that it has a splitting over the algebraic closure? Like,
yeah, or even the perfect closure, yeah. Okay. Yep. Yeah, so if you want smooth connected unipotent. Then there's more general, like, you could have like alpha p is considered unipotent, but whatever. OK. So, great. So the point is that the move from the Sansuc reductive case, which still works over function fields. Sansuc's proof still works over function fields if you assume G is reductive. But the move from the reductive case to the general case is much more difficult in the function field setting. This is one of the very few cases where function fields are actually harder than number fields, right? Usually it's the reverse. OK. And well, I mean, there's a good reason that the move is hard. It's because Sansuc's formula fails in general over function fields. And in fact, it fails very badly. So pick G need not be finite. So for example, if U is a non-trivial, this is a non-trivial form of GA. So if the form of GA over, in any imperfect field actually, not just function fields, over an imperfect K of characteristic P bigger than 2, then U cross U has infinite Picard group. So you can find such examples. So this produces such an example whenever P is bigger than 2 over whatever imperfect field you want. OK, so it fails very badly is the point. But this isn't so surprising. I mean, the formula up there, is it still up there? Yeah. So up there has a certain asymmetry between the 3 objects. So the Tamagawa number of G, of course, defining that used the group structure very essentially. We chose a left invariant form. And we used, we had to take quotients. Like the group structure is all over the place in the definition of the Tamagawa number. And similarly in the definition of the Tate-Shafarevich set, we use the group structure. But the definition of pick just depends on the scheme structure. It didn't remember the group structure at all. You're just looking at line bundles. You don't remember the multiplication map at all. So the object pick G is sort of not natural. So how do we replace it? So we want to replace pick G by something else, which remembers the group structure. OK. And so the object we take is the following. So we define x1 of GGM. And by the way, this definition actually, G doesn't have to be linear here. So this is for any smooth connected G over a field K. The smooth connected group G over a field K. So we define this to be the set of line bundles such that L is universally translation invariant, modulo the base. So it's in quotes, translation invariant mod the base. So another way of saying this is if you have the multiplication map and the 2 projection maps, pi1 and pi2, from G cross G to G, then M star of L, so you pull back under multiplication, this should be isomorphic to the tensor product of the 2 pullbacks. So that's X, and that's, of course, a subgroup of the Picard group of G. OK. Right, so maybe I'll leave this up. So of course, if we want that, I mean, OK, so the idea now is, you can see where this is going. I just replace pick with X. And well, there's several things you have to say about that. So first of all, if that's going to be reasonable at all, we had this problem where pick G could be infinite. So the X group had better be finite if it's going to be a useful replacement in any way for pick, in terms of proving a Sansuc type formula. So here's a proposition. If G is a connected linear algebraic group over K, which is a global function field, then x1 of G, GM, is finite. OK. So yeah, I'm about to make a remark here, yeah. Yes, no, it's not clear, but it does, OK, so here, remark. OK, so if K is perfect, so for example, a number field, then for any connected linear algebraic K group G, x1 of GGM is the full Picard group. Every line bundle is translation invariant, and this group is finite. So it recovers Sansuc's formula in the number field case. So that's one. The second thing I should say is this proposition is really an arithmetic statement. It fails, for example, e.g., over every local function field. So if you replace global with local, this proposition is totally false. So you need to use arithmetic somewhere. All right. Yes. OK. Right. So now let me, do I have time? Well, maybe I'll just very quickly say, I don't know if I have time to do this, but there's an analogy with the BSD conjecture here. So maybe state this very quickly. Suppose that A over K, which is a global function field, and A is an abelian variety. And let's assume for simplicity that A has rank 0. OK? So then you might say, well, how would we define the Tamagawa number of A? All right. Well, I mean, again, you want, of course, it to be the volume of the adelic points mod the K points. So what is this? Well, because A is proper, the adelic points of A are topologically the product of the local points over all V. And so if you want to compute this volume, what you basically want to do is compute the volumes of all of these, multiply them, and then divide by the number of K points. OK? So what is the volume of A of KV? Well, let's say that script A is the Néron model of A over E, or associated, the curve associated to this field. So this is the volume of the OV points of script A. And what is this? Well, I mean, for each residue point, so you get, this is the special fiber, and you get the number of residual points. And for each residual point, you have something that looks like MV times MV, MV the maximal ideal of OV, where this is G copies. G is the dimension of A. OK? So you should get the number of points over QV, which is the number of points of FV to the G. G, again, the dimension of A. And this is the number of points in the connected component of the special fiber times, well, it's called CV, the Tamagawa factor, and this is defined to be the size of AV mod AV naught. So this is the étal component group, and you take its FV points. OK? So it's that divided by QV to the G. And it turns out that this number right here, this is none other than the local L factor of A evaluated at 1, but inverse, times this Tamagawa factor. OK? And so now, what should the Tamagawa number be? You should just multiply this over all V and divide by the number of K points. So we could say Tamagawa number of A, let's just take it as a definition for our purposes, although you can make this better than just a definition. But this equals the product over all V of the L factors, that's just the L function, evaluated at 1, inverse, times the product over all V of CV, the Tamagawa factor, and you divide by the number of K points. That was why we assumed that A has rank 0. OK, and we'd like to say, well, is this equal to the size of x1 of AGM, right, by analogy with the fixed version of Sansuc, where we replace this by x. Is this the size of this over the size of SHA of A, which, of course, is conjecturally finite? Now, by the Weil-Barsati formula, this is none other than the K points of the dual abelian variety. So AT means the dual abelian variety. And you divide by the size of SHA of A. OK, so we want to know, does this equality hold between this thing on the left and this thing on the right? And this is exactly rank 0 BSD, including the non-vanishing of L at 1. So this is rank 0 BSD. OK? So this formula with X is the exact linear algebraic group analog of the Birch, Swinnerton, and Dyer conjecture, which is another reason you might expect this to be true.
Notion of duality for these crazy unipotent groups in this setting where your x is like the k point, the global k points of something?
No, but no. But you can, I mean, okay, you can construct varieties which embed into the x of these u's if u is like a form of GA. So this is done in a paper of Bert Totaro. I forget what it's called, but yeah, I think pseudo-abelian varieties or something is the name of the paper.
Perhaps you could say that this is due to Spencer Bloch.
Oh yeah, sorry, yeah. So this is due to Bloch, and not only is it due to Bloch, but he makes this analogy more precise rather than this weird ad hoc thing, and he extends it to positive rank abelian varieties, not just rank 0.
So you mean the definition of this x is due to Bloch?
No. This analogy with BSD.
Okay.
Yeah.
But is it precise to the rank 0 BSD, or just, I mean, because you're going into 1 at a point and then expanding at a point where it's like non-convergent. Right? I mean, you're pointing at a value which is beyond the...
Yeah, no, okay, yeah, sure. I mean, yeah, so you're assuming that it's defined at 1. Yeah, no, yes, that's true. Yes. I mean, I think this is, okay, we can talk about it after, but I think this is rank 0 BSD, whatever. Okay. Okay, so now I'll start talking maybe about results. I have about 10 minutes left. Yeah, I'm assuming K is a global function field, just so I don't have to think about anything Archimedean. Yeah. So I said there, K is a function field. Yeah. I mean, I don't want to get too much into this thing. I was just mentioning it as an analogy. Like, this should tell you that this is somehow the correct formula. It's the thing that should be true somehow. Okay. So theorem, I'll say theorem 1. So if G is pseudo-reductive over K, which is a global function field, then this formula holds. Okay. Right. So I can't explain the proof of this in any detail because it's very, very long. But I can maybe say 3 black boxes that go into the proof, which are sort of the 3 key ingredients. Okay, so 3 key ingredients. So one is the classification of pseudo-reductive groups by Conrad, Ofer Gaber, and Gopal Prasad. Okay, so they give a classification of pseudo-reductive groups over arbitrary fields, which basically explains how to build an arbitrary one in some explicit way out of simply connected groups and commutative pseudo-reductive groups. So the commutative case, they can't really say anything about. Commutative groups are just blobs about which, basically anything that can go wrong with them does go wrong, so to speak. So this is, I'll say, up to simply connected plus commutative groups. But I should say there's a lot of work that goes into using this classification to reduce to the simply connected and commutative cases, particularly in characteristics 2 and 3. There are these exotic groups that show up that are related in some not very, some not totally explicit way for our purposes to simply connected groups. So you do have to do, this is a lot of work to reduce to simply connected and commutative groups. Then, of course, the second ingredient for simply connected groups is Weil's conjecture, which is proved over function fields by Gaitsgory and Lurie. Okay, so that's to handle this. And then for commutative groups, as I said, they're just blobs, so you have to have some very general facts about commutative groups. And so the key point is there's this classical Poitou-Tate duality. Tate duality, so you have local duality, and the 9-term exact sequence is the key point. In particular, so classical Poitou-Tate duality is for finite discrete Galois modules, which are like finite étale group schemes. And recently, I think in like 2015 or something, Kęstutis-Czesnevicius generalized this to arbitrary finite commutative group schemes over global fields, like over a global function field. So he went from Galois modules, which are finite étale, to arbitrary finite group schemes. And then I recently generalized this to, so first you have Czesnevicius. Sorry, I don't know where the accents go. Is it here? OK. So he did to finite commutative group schemes. And then recently I generalized this to all affine commutative group schemes of finite type over global fields. So in particular, this includes connected linear algebraic groups. So like commutative pseudo-reductive groups, say. And so you use a result of Oesterle combined with just the 9-term exact sequence, and the desired formula for commutative groups just sort of pops out. Right. OK. Great. So those are the three main ingredients. I should say this is all very long. Like the proof of this generalization is like over 200 pages. So it's a lot of work that goes into proving all this stuff. OK, so I have like 5 minutes. So let me talk about what about beyond the pseudo-reductive case. And the answer is everything goes terribly wrong. So for example, in any characteristic, there exists two-dimensional. And of course, they have to be non-commutative, because this holds for pseudo-reductive, I should also say, and commutative by this Poitou-Tate stuff. So there exists two-dimensional non-commutative wound unipotent groups. Wound is like the analog for unipotent of anisotropic for tori. Wound unipotent groups in any characteristic, over function fields of any characteristic, such that theorem 1 fails. So the analog of BSD fails. But things get much worse. So a key point in the proof of Weij's conjecture over number fields by Langlands, Lai, and Kottwitz, and this is the step Kottwitz did, is to show that Tamagawa numbers are invariant under inner twisting. That was sort of the last step that finished the proof. So you might wonder, is the same thing true in this setting, so over function fields? And so second result is if G is pseudo-reductive, or of course commutative is trivial, but if G is pseudo-reductive, then Tamagawa number of G equals Tamagawa number of G prime for any inner twist G prime of G. OK, so for pseudo-reductive groups, everything's great. But again, if you pass to these non-commutative wound things, then so over every global function field, there exists the usual wound, two-dimensional, non-commutative unipotent groups U such that the following holds. For any epsilon and m greater than 0, so you should think of epsilon as being tiny and m as being really big. There exists an inner form u prime of u such that the Tamagawa number of u prime is less than epsilon, and simultaneously the size of the Tate-Shafarevich set of U prime is bigger than M. Okay, so this gets really tiny and this gets really big. So it's certainly not invariant under inner twisting. So I should say that, so this has implications for this local to global, or this global to local map. So if you have H1KU to the product, actually goes to the coproduct of these H1s. So the Tate-Shafarevich set is by definition the fiber above the trivial element here. But you might ask, well, what about the other fibers, right? So for an elliptic curve, the non-empty fiber is all of the same size because everything's just, it's just a map of groups. But here it's just pointed sets, so a priori they don't have to have the same size. So if I have an x in here and I ask which elements live in the same fiber as x, then you can twist by x. And that tells you that this is, so the fiber containing x is in bijection naturally with, well, okay, it's in bijection with the Tate-Shafarevich set of some twisted inner twist use of x of u depending on x. Okay? So this statement actually implies that for these weird groups u, these weird unipotent groups, this map has arbitrarily large fibers. Whereas for pseudo-reductive groups, I didn't say this here, but if G is pseudo-reductive, not only this, but also the Tate-Shafarevich sets of the same size. And so if G is pseudo-reductive, the non-empty fiber is all of the same size. So the last thing, which I probably don't have time to say because I'm out of time, which I'll mention is, so you have this map, and in trying to understand this question beyond the pseudo-reductive case, you're naturally led to ask, well, which fibers are non-empty? And there's a simple exact sequence. You just say this goes to something else, some finite group, which tells you exactly which elements here are hit by this. So that's when G is pseudo-reductive. There's a way to determine which fibers are non-empty. And once again, that thing which works for pseudo-reductive and also for commutative groups completely fails for these weird unipotent groups. So basically, the motto is everything goes wrong for these unipotent non-commutative groups, whereas everything is fine in the commutative and pseudo-reductive cases. OK, so I'll stop there.
Any question or remark?
Is the X1 G GM, is that invariant under inner twisting?
Yes, that's for any G. It doesn't even have to be linear. That's invariant under inner twisting. Yep, over any field. Yep.
I saw one up there.
In practice, how practical is it to compute these sizes of X1 and of SHA-G?
Well, OK. In practice, you can, OK, so in practice, the group you have will typically have some sort of presentation as like, you know, you take some simply connected thing, maybe you take a Weil restriction, you take some semi-direct product, and you take some quotient. And when you do that, there are exact sequences which tell you how this X can be computed from such a presentation, and similarly for this SHA. So in practice, you can do this, well, for let's say pseudo-reductive groups. For unipotent ones, well, this you can actually compute because x1 of G will be the same as x1 of the abelianization of G, for G unipotent at least. And this maybe is a little hairier to understand. And this also is a bit hairy to understand for these weird non-commutative unipotent things.
More questions? Yes?
What goes into the proof of theorem 2? Can you?
Theorem 2, which is what?
About inner twisting.
Oh, this thing.
Yeah.
OK. Yeah. Again, so it's actually the opposite. So the proof of it, so classically, over number fields, to prove that Weil's conjecture, you first prove invariance under inner twisting, and then you deduce Weil's conjecture from that. This goes in a sort of opposite direction. You use Weil's conjecture in an essential way to effectively compute these things, and then you determine how they move, how they change under inner twist, right? And of course, a key point of that is going to be something like, well, you need something more general, but in particular, if I have a simply connected group and I inner twist, it's still simply connected. So the Tamagawa number is still 1, right? And of course, commutative groups don't change under inner twisting. So, you know, there's some involved devisage from those cases, but roughly speaking, that's how it goes, yeah.
Other questions? If not, let's thank the speaker again.